This is the Snowy River National Park. It is a vast and magnificent landscape. But even all that we see here is just a tiny part of the Earth's crust. We can walk this country and study these rocks and imagine the massive forces that raise these mountains. But unless we look deeper, kilometres below the surface, we will never know the full story of how our continent evolved.
Yep, that's right. There's literally 100 million years of geology sitting in this bit. It's like time travel. It's really pretty well defined here, and suddenly where's it going? It's really interesting.
It's pivotal that we've got people with really sound and solid field experience that have seen these rocks, but we've also got some of the newer generation too, which are unbelievable at taking some of these data sets and pulling them together, and it's that coalescence of skills and knowledge that is helping us get the most out of the interp.
The interp that Cameron Cairns is talking about is the interpretation of a massive amount of new data. This data will help to reveal the land's ancient origins. Understanding the composition of the deep crust has long been a quest for Australian geoscientists. But now, with new tools and a collaborative approach, they've made it possible. The Geological Survey have always been able to study rocks near the surface, like these. But to truly understand the origins of the land, they needed to look deeper than ever before. Not just a few kilometres, but tens of kilometres down. To do this, they needed help. So the Geological Survey of Victoria brought together the resources and expertise of Geoscience Australia, a scientific group called AuScope, and the Geological Survey of New South Wales. Together they share a common goal: to understand the geological architecture of the southeastern part of our continent.
One of the things that academics in Australia are particularly interested in is the evolution of the Australian continent, and to be able to analyse that and do research into that, they need to be able to image the very, very deep parts of the continent and look at what the building blocks are that came together to create the Australia that we know today.
These geoscientists are investigating the origins of southeast Australia.
It's almost like a diffuse zone building here, isn't it? Something quite diffuse rather than...
Okay, we have theories about how the continent's put together, and we have models based on that, based on what we can see on the surface. But you don't know how they are connected at depth.
The connections between surface and buried rocks is commonly revealed using gravity and magnetic data. Dr. Bob Musgrave is a senior geophysicist with the Geological Survey of New South Wales, and he saw something in new magnetic data that was quite remarkable: a huge curve in the rocks on a continental scale. This inspired Ross Cayley from the Geological Survey of Victoria to start thinking big.
Imagine this edge of the water here is East Coast Australia, where we're standing today. So the coast sort of heads down to Wilson's Prom, and Melbourne's in here, and Western Victoria's over there. We started a survey north of Melbourne and we proceeded all the way to the east coast.
Ross realised that Bob's revelation could explain some perplexing rock structures recently mapped in Victoria.
And the idea we were doing that was to test the idea that we've got geology that's wrapped in a giant fold at Victoria scale.
When Ross combined Bob's data with the Victorian mapping, what he saw was almost unbelievable. New South Wales and Victoria seem to be part of a huge fold called an orocline.
The Lachlan orocline model suggests that about 430 million years ago, these giant vertically plunging folds with amplitudes over 1,000 kilometres were formed in eastern Australia.
A byproduct of large folds on the scale of an orocline would be vertical faults. And the Geological Survey has actually mapped some vertical faults at the surface. But if formed by an orocline, they would be huge and extend all the way to the base of the crust. So how does a geologist explore the Earth's crust on this scale? I could look at the outcrops in those mountains behind me to try and work out what lies immediately beneath my feet. I could even drill a diamond drill hole down 1 kilometre or so. But to work out the structure of the deep crust, down to say 40 kilometres, then I need something very special. And it's called a seismic reflection survey. The trucks lower their pads and start vibrating. And this creates energy enough to send waves down through the Earth as far as 40 kilometres or more. And the waves bounce back from layer upon layer beneath us until they reach the surface in a matter of seconds. This technology is just like an ultrasound scan, but this scan is on a huge scale, and the source of energy is the vibroseis trucks, or VIBES. These giants may be large, but they have a tiny footprint.
It's a listening technique. So there's an array of microphones that we've pressed into the ground, one every 10 metres, and they're laid out for 6 kilometres in front and behind where the trucks are operating.
The tiny companions to the giants are called geophones, specialised microphones that listen to the Earth.
And even though the tracks here are really difficult, we've been really lucky because we're getting the acquisition done and we've got absolutely perfect weather and it's completely quiet. The only thing you can hear are birds chirping and flies buzzing, and that's not a problem for the geophone.
Without interference from wind and rain, the geophones are able to listen for the tiny vibrations reflected from buried rocks. By combining all these reflections, a gigantic vertical image of rock strata is created. And the team is hoping they'll find evidence for the huge folds already seen in the magnetic and mapping data.
And the formation of these folds involved geology being transported south by thousands of kilometres. And we should be able to see these patterns in the rock record right down to 40 kilometres depth. So it's only still a preliminary interpretation, but you can see there's some very distinctive reflectivity here that changes markedly in character to the west. And so it is possible to draw subvertical faults heading down, right down into the lower crust, in fact.
These huge faults have been a mystery since they were first mapped in the 1960s, but now they might be explained by the orocline model, which theorises a massive southward motion. As crust was drawn southward, it began to wrap around the much older Tasmanian crust. This movement forced adjacent areas to shear, thus creating the deep vertical faults. The team targeted features like these when planning the survey. So if they can produce detailed enough seismic imagery, it will be a powerful tool to examine the formation of southeastern Australia. There's only one problem. The trucks must cross the continent's most mountainous region, the Great Dividing Range.
And the idea is that we want to shoot seismic over the geology that gives us the best chance of solving the scientific questions we've posed for the project. It's hilly here, and so the rocks we want to study stick out of the ground. So we've already looked at the rocks directly as geologists, and now we can take seismic data to take the understanding deeper.
When the surface geology is well mapped and well understood, it is easier to extend that knowledge down using the seismic data.
So what we want to do is try and thread the needle between geology that's meaningful and tracks that allow us to image it in the best possible way.
To create images like this in such mountainous country, the team needed a new technology that was both flexible and lightweight.
With the node system, it can be plugged easily. Around here, there is a GPS receiver.
As well as the seismic data, each node records its own GPS position and time.
So the timing accuracy, even every millisecond, is very important.
The depth of different strata is calculated using the delay time of reflected waves.
The feature of node is designed as tough.
In a never-ending dance, a large crew keeps the nodes moving along with the vibes. The chief choreographer of this dance is Ryan Newbold.
Dig that in, kick that in, tremble it, whilst the vibrator is still doing Pac-Man style.
That's right, it's like Pac-Man.
Yeah. Pretty
His position at the head of the procession means he is often the one who encounters the general public.
Over the last, say, 10 or so years, where all these little blue lines are, they've done seismic surveys. And this is the last one to sort of piece together their puzzle of what's been happening over the last, say, 500 million years.
Earlier surveys have already tested Western and Central Victoria, giving us an entirely new understanding of Victoria's geological architecture. So to complete the survey of Victoria, the 2018 line crossed the Australian Alps and finished on the east coast. This will build on earlier work to help us understand the formation of Southeast Australia. It will also help with more modern scientific questions.
So does this warn us of stuff in the future? Is that what it's doing?
It could as well, yeah, for sure.
And one of the reasons we're interested in understanding the geometry of the faults is because they can contribute to understanding the earthquake hazard for the region, and that might be important for developing management plans for reservoir dams and that sort of infrastructure.
Surprisingly, the Victorian Alps is a young and dynamic landscape. Some uplift happened as long as 80 million years ago, but most uplift is very recent and is ongoing. In the last 6 million years, the Pacific Plate along New Zealand has been pushing towards Australia. The Australian Alps are rising further, reactivating ancient faults and causing occasional earthquakes.
So we think of Australia as being a very stable continent, but we do know that there have been some very significant earthquakes in Australia in recorded history and in human history. In fact, not too far from where the survey was taken, there was a very, very large earthquake about 40,000 years ago that dammed the Murray River. So understanding the deeper geology may allow us to get a better understanding of some of the faults that might be active in this region.
Trembling. So I'm going through and making sure the nodes are in the correct order and all accounted for, and if there's any issues, catch them. Compared to the usual places that we work at, this has been really beautiful. We generally just get to see the flat parts of South Australia, so being in the Victorian Highlands is a nice change. Walking, 6 to 7 kilometres a day, Trimble.
The new nodal technology meant that this survey collected more data than any previous onshore survey.
This is the harvester truck. So this is where everything gets downloaded and collected. So we have in here the battery charging station, and the data downloaders.
Hundreds of nodes are processed every day. Once disassembled, the node's data is downloaded and it goes to Nelson for cross-checking with the Trimble GPS and time data.
So as soon as they come off the rack and if they're downloaded, we check to see that everything matches.
Nelson then passes the data to Lewis for quality control. And because the nodes are left out overnight, they also record natural seismic activity, resulting in a massive amount of new information for the team.
And if everything they say they brought has been downloaded, that's it. The load gets put together, assembled, and out the door it goes again.
The main use of the seismic data is to visualise large-scale structures in the Earth. So features like mineral deposits are usually too small to be seen. But by understanding the evolution of the continent, it's possible to have a much better understanding of the formation of those resources.
So there is a case for doing this in support of the exploration industry, but the research questions are really much bigger and really relate to how continents evolve, how mountains form, how continents get torn apart during extension.
If the orocline model is correct, another byproduct of its movement is crustal extension. And when that happens, the crust becomes thinner and can even create an area called a rift, which could be a broad valley. And because the crust under the rift is thin, it allows volcanic material to come to the surface, filling parts of the rift. And the rift can sink, and so the sea can invade, depositing marine sediments and even limestone. And this is exactly what's happened in the Buchan Rift area of eastern Victoria 400 million years ago.
Well, this is the first time we've been able to have seismic reflection data available to test ideas like the formation of the Buchan Rift. So we have some surface control on where the rift is. And now, with this seismic reflection data, we can actually see the quite reflective rift fill continuing down to this position here, marked in blue. So this is the first time we've actually had evidence that shows us what the shapes of this rift really looks like.
So the reflection seismic gives us that incredibly detailed transect through the geology. You can't understand the geology and the history of a continent if you don't have that three-dimensional component. It's kind of like trying to understand what the human body would look like without having X-rays or MRI machines.
With the sort of scale of seismic data we collect, full crustal, you'll have a 3 metre long section to look at 1 to 100,000 scale. But if you want to get the big picture, you really need paper. It's an old-fashioned way of doing it, but it gives you much better control over the big structures, which is what we're looking for. Well, these surveys always give us surprises, and that's why we do them, because we don't know what's there, and we're learning stuff all the time.
And what's interesting is that there are additional subvertical changes which we haven't actually recognised in the geology before, even within the Tabarabra zone. We know from the mapping that there's a terrain boundary between old crust with Tasmanian affinity at depth and to the west, and younger crust with oceanic accretionary affinity to the east. And this interface, which seems to be some sort of fault combination of the two different terrains pushed towards the surface and towards the west, that is just simply world-class imagery in seismic reflection data.
There's nothing better than getting around the maps and sections with pencils in hand and having a robust debate with colleagues about what it might mean.
Something as low-tech as coloured pencil to paper seems to be the best way to synchronise the creative and very technical skills of the team. For example, geophysicist Dr. Alison Kirkby is an expert in what's known as magnetotellurics, which measures the electrical properties of rocks at the scale of the continent.
This image here tells us about how well the rocks reflect sound. But the resistivity is a different property. It tells us how they conduct electricity. So it's an independent constraint on the rocks. So you might have two different rocks that are very similar in the seismic. If you have the resistivity, then that might be able to highlight differences between the two.
So different geophysical techniques are used to measure different properties of rocks over large areas. Gravity data can be used to check the density of rocks. Magnetic data can help to distinguish packages of rock in a seismic section that otherwise look the same. And so all these methods complement the seismic data, helping to build a more accurate picture of the crust over a much broader area.
It's max. Well, probably it's a limit.
Yeah.
In some sports, it depends on.
This has to have been one of the most challenging onshore seismic surveys completed in Australia. Seismic expert Tanya Foman had to carefully assess all the challenges.
When we looked at the routes on the map, I thought it's not possible to do it all.
When Tanya and the team got on the ground, they realised that with the help of land managers, local experts and communities, it was possible to design a safe route despite the rugged terrain.
Everything has come together. So we've got a very good team in Victoria, very good team in New South Wales, in the Canberra, in the Geoscience Australia as well, people who actually wanted to actually make it happen. Plus we have very experienced contractor.
Well, yesterday we found out there was a oil seal leaking on the drop box. So we changed the uni because there was a little bit of play.
Oh, great! It's been a challenge, and you know it was a long job, but we stayed busy and it went quick. Why are they doing this job? To give them a bit of an insight onto how the Earth moves.
Monday, Tuesday, Wednesday, yeah. I have to breathe in after fly home, back to France, and I say I take 3 months break.
Pretty much a staple sandwich all across Victoria and New South Wales. Cheese, chutney, ham. Cheese, chutney, lamb. Cheese, chutney, beef.
Oh, look, it's a sort of a mixture of excitement and relief in a way. So relief that the project went so well. We had to have a lot of things go in our favour. We were blessed with really good weather. We had a fantastic crew, and the logistics just panned out really superbly.
Here you go, the last one. It's my honor to lay out the last note. No worries, mate. Thank you. Here? All right. Very last one. This is all for science.
The exciting part is now we've got in the can heaps and heaps of fantastic deep seismic reflection data. And we can use this data, that's what we anticipate, to test all these geological and geodynamic models for Eastern Australia and Victoria specifically that we've been working on for years and years. It takes lots of people to pull something like this together, and you know, if anyone drops a ball it doesn't work as well as it could, and everyone really hit the ball out of the park with this one. Just like at the start of the survey, we get to see the results from these nodes and compare them to the rocks that stick out of the ground, and that's been the whole purpose of the whole thing. From the acquisition crew to the design, the processing. So we have to sort of do justice to it now with a really good geological interpretation.
With these data and results, the team can assess the orocline model. They've seen the massive vertical faults, and now they see something else that may have driven the orocline itself.
Now what's exciting about this is that this region is of oceanic character and is dominated by early west dipping faults, and you can see some of those in the seismic data. And unbelievably, below the base of the crust imaged here at about 12 seconds, we can see the faintest hints of possibly a fossil subduction zone trace dipping to the west underneath. And we have to do some more work to confirm if that's the case. But if that's true, this is a really fantastic result, because that is the geodynamic driver for all this structure.
For the first time, the team have extraordinary seismic images that extend more than 40 kilometres below southeast Australia. These images will be combined with other geoscience information, and together they will test the orocline model and its influence on the geology of our continent. This amazing data was collected from the placement of 63,000 geophones across the mountains of southeastern Australia. Applied geoscience like this enables scientists and everyone to understand faults, earthquakes, potential resources, and the evolution of the place that we live in.
Just absolutely wrapped, ecstatic. We've just travelled 629 kilometres from the Murray Basin, south of Benalla, across the Great Dividing Range, and we find ourselves now on the east coast of Australia, on the Tasman Sea. We can really start putting the final pieces of the jigsaw into place on how Victoria and southeastern Australia has evolved from an ocean 500 million years ago to the landscapes that we see today, including those mountains of the Great Dividing Range.